Good afternoon. Today we're looking at observer design. In the previous lecture we looked at pole placement design, and this was the example we looked at a pole placement for controller for. So we're going to use the same example within the observer design. Let's just take a quick look at the observer. This part here is the original system, so that's going to be this transfer function here. It's inside here. Normally we'd have a state feedback controller around there giving us the desired closed loop poles. In some cases though, not all the measurements X are available. So we have to then in that case use an observer to generate some of the variables that are missing from these state space equations. And this then is the structure of our observer. So we have a parallel model. This is a model now of the real system running alongside the real system with the same input going into it. And we'll have to design these state space equations. So our design parameters will be to design A hat, B hat and C hat. So they're our first things that we'll need to be able to design. Then we've got to be able to design a feedback controller L that guarantees stability of this system and guarantees that the error signal in the system goes to 0. This ensures that the observer values and the real values coincide. And then the final thing is we have to design a transformation matrix, because these state space equations are not the same as these. So I have to transform these states into these to use for the full state feedback controller. So we have two extra parameters to design, L and T. So in the overall design of an observer, we will need to represent this diagram and then work at A, B, C, L and T. So let's start off with this. A good starting off point would be to work out some corresponding state space equations for this system here. So our best option is to do it in companion form. So you could have, say, x1 dot, x2 dot, x3 dot is equal to, there'll be some matrix here now, times x1, x2, x3. That'll be u feeding into this. So we put 0, 1, 0, 0, 0, 0, 1. So that's our standard companion form for a 3x3 system. Then put these numbers here in reverse order on here with negative signs. So it's going to be minus 72, minus 54, minus 13. And the output y will be given by 12, 6, 0. So that's times x1, x2, x3. These numbers here come from these numbers again in reverse, so it's going to be, but this time with positive signs, 12 and 6, 12 and 6. So these now represent our state space equations which go in there. Next thing we've got to do is to design our observer. Now this is very straightforward, because what we're going to do is use the transposed system. So what we do in the transposed system is, if we've got state space equations, x dot is ax plus bu, y equals cx, we convert these into x dot hat is a transposed x hat plus c transposed u, and y hat equals b transposed times x hat. So we have basically, this is our observer design here, and we get this quite quickly from these three matrices. We just transpose this one, put it there, transpose this one, put it there. So that's going to give us the first part of our design, A, B and C. And so if we get the A hat, we'll put them down here. A hat is going to be a 3x3 matrix. And it's basically going to be this matrix here transformed. So it's going to be 0 or transposed 0, 1, 0, 0, 0, 1, and then minus 72, minus 54, and minus 13. So that gives us our A hat. To get the B, which is going to be C transposed. So the B is going to be this transposed. So it's going to be the B hat is going to be 12, 6, 0. And the C hat, which will be a 1 by 3, will be this one transposed. So that's going to become 0, 0, 1. So there's the first part of our design concluded. That's getting the state space representation for our observer. That's this A, that's the B, and that's the C, corresponding to those particular parameters. The next stage is to design the L. So we'll just make ourselves a bit of space here. What we're looking for is when we use this feedback in here, we're going to end up with a matrix A hat minus L C hat. And we want the eigenvalues for this to have some negative values. So the eigenvalues of this are important. And we want this system to be faster than this system here. So any changes that go on in the real system, the system can track. So we're going to have some L that's going to put some closed loop poles into the system for us, which are significantly faster than these. So I've decided to choose, and these can be chosen to some extent arbitrarily. I've chosen 3 fast poles. So I've got an S plus 50, an S plus 80, and an S plus 100. There's 3 poles because this is a third order equation. Then what I have to do is expand this out now into a polynomial. So if we expand this one out, it comes out as S cubed plus 230 S squared plus 17,000 S plus 400,000. That's quite big numbers. You can check some numbers quite quickly. That one's going to be that plus that plus that, which looks okay. This one's going to be that times that times that, which also looks okay. You can also do that as well, but that's the polynomial that we get when we expand those out. Now, in designing L, we go back to this equation here, and the state feedback controller is going to be of the form L now. It's going to be from L1, L2, L3. That's the format of our state feedback controller L. And we need to work out L1, L2 and L3. Now this can be done by going back to this equation here, and because it's like a reverse order method, we can rewrite this equation as S cubed plus 13 plus L3 S squared plus 54 plus L2S plus 72 plus L1. So what we do is we add in the L1 gets added into this number, the L2 onto this one, and the L3 onto that one. Now what we can do is these 2 equations, this represents the closed loop state space equations here, and this one represents the desired closed loop equations. So these 2 equations have to be the same. So that means that this parameter here is the same as that one's the same as that one, and that one's the same as that one. So that gives us 3 little design equations now, which is that 400,000 equals 72 plus L1, 17,000 is equal to 54 plus L2, and 230 is equal to 13 plus L3. So these now are quite easy to solve. We just subtract this from that, subtract this from that, and subtract that from that to give us L1, L2 and L3. Right, so we can now solve these for L1, L2 and L3. So we'll get the L, we'll put them here. L1 turns out to be 3, 9, 9, 9, 7, 8. L2 comes out as 16,946, and L3 comes out as 217. So that now gives us the next part of our design. So we've now got L1, L2 and L3. So that's the parameters near L1, L2 and L3 that go in this feedback control system. So we've now got A hat, B hat, C hat and L. The final thing now is to work out the T. Now the T is a transformation matrix which converts these into these. Now what we know is that if we use, so we now need to compute the T matrix. So the first thing we know is that if we've got any state space equations, we can convert them into companion form, which is what this one's in, by using the controllability matrix. So the controllability matrix is given by B, AB, A squared B. But it's also has to be multiplied, so T, by a further matrix called W, which I'm going to explain in a second. So this is the equation now for T for this particular case, because it's a third order system between B, AB, A squared B. But this A and B are in fact these here. So in fact, this is going to be B hat, A hat, because we're having to use the observed values. So we'll now compute this. So B hat is going to be 1260. It's going to be 1260. That's the first column. Then we're going to have to multiply this by this to form AB. And that comes out as 0, 12, 6. Then we have to work out A squared B, which is this times this. And that comes out as a slightly bigger numbers here, minus 432, minus 324, and minus 66. So this is getting towards now RT. That's B, AB, A squared B. We also need to introduce a W. Now, the W for this particular system, if we think of this as being A0, A1, A2, and A3, we have to introduce a W matrix in here to finish off the transformation. And this one has A2, A1, 1, A1, 0, 1, 0, 1, 0, 0. This is the W matrix. It's basically filled up with ones there. This part is 0, and this part here is that, these coefficients here. So it's not that one, it's those two. So it's the, ignore the last one, that becomes A2, A1, and that becomes A1. So we'll have to pick up those parameters now from this matrix. So A2 is clearly 54 and A1 is 13. So there's the equation now for T. So we can now multiply this by this and then we'll get the T matrix. So T comes out as 216, 156, 12, 156, 96, 12, 6, 0. And this matrix now will transform the states from the observer companion form into companion form for us. And that is then the complete design. So we've now got, in this design, we've got the observer, A hat, B hat and C hat. So those are going to be given by A hat is that transposed, B is that transposed, and C is that transposed. That gives us this bit of design. We then go on to design the L to get the L parameters, which I've just shown you. And then this last stage is to use the controllability matrix plus this W matrix to generate the T matrix. And this is the transformation matrix then, which converts these through. And interestingly enough, if you want to have a go at this, if you work out, if we T times A hat times T to the minus 1, if you compute that matrix, you'll find that comes out as A. So that's showing that the overall calculations have been done correctly. So that's a little check you could do in MATLAB because this could only be done in MATLAB because you've got to invert this matrix T. But so that could be a final check if you've done this for real, to check that that matrix there did in fact come out as the original A. And that then is the overall design of an observer.
Okay, here's an example of the MATLAB code. Here I've defined the A matrix. This is in companion form. This is the B and this is the C. I've then computed B, AB, A squared B. I've then put those into formed the controllability matrix here and then worked out the W matrix. I've then multiplied the controllability matrix by the W matrix to give us the transformation matrix, and then I've computed the companion form of the state space equations now as the inverse of this matrix multiplied by the original observer companion form matrix multiplied by the matrix. And what we should find out then is this is in the A is in observer companion form, but this part here is actually in companion form, showing that the transform is correct. And if we run the code, we would get the following results. So if we just scroll up here, I've got, here is my A matrix, then there's the different parts of my controllability matrix. There's my overall controllability matrix. Then I worked out my W, then it's worked out the transformation matrix, then it's then computed this term here, and there we have the final A matrix in the correct companion form.